Hey, welcome back. Um, in this video, we're actually going to be starting on confidence intervals, which is probably the most important topic in Chapter 7 of our elementary statistics book. So Chapter 7 has a variety of topics, but for our class, we're going to be focusing on confidence intervals. So confidence intervals can be used to estimate. The word estimate in math essentially means make an educated guess. So we can use a little sample that we have to guess or make an educated guess about an entire population. And we'll actually know, after we do the math, we'll know how sure we are that our guess could be correct, and also how sure we are that it might be not correct. As with any other guess, though, it's still a guess. But the cool thing about it is when you're making a confidence interval, your guess is not just educated, but you have the math to back it up, so you know your chance that your guess is wrong, and you also know the chance that your guess is right, which is known as your confidence level. Okay. So anyway, we're going to be focusing on 7.1 in this video. It's a long section, so I'm going to try to have to move through it more quickly and do less board work than I usually do in my videos. Most of the stuff is worked out in detail on the slides, so I'm just going to kind of go through most of it, and then I might write a little bit on the board, but this video is probably going to be long if I write too much. All right, so in this section, what are we going to be learning about? Well, there's quite a bit of stuff, but we're going to present methods for using a sample proportion to make an inference about the value of the corresponding population proportion. Now, think of the population proportion as P, okay? That's the same idea as a population proportion P, where P is the probability of a success in a single trial, or at least that's what we're used to from the binomial distribution. So it's sort of the same idea here. But instead of being the probability of a success, it's the probability that a randomly selected data value is a success. So it's kind of the same thing. So that's the population proportion P. We'll talk about that. And then in order to estimate or guess about the population proportion P, first we need to focus on a very rough guess called the point estimate. So the point estimate is the sample proportion P hat. That's considered the best point estimate of the population proportion P. Obviously, unless we can do a census, we aren't going to know the population proportion P, but we are going to know the sample proportion P hat, which is very easy to calculate. It's just X, which is the number of successes, over N, which is the number of trials. And if you're lost with any of this terminology, make sure you go back and review section 5.2, because I talk about P and Q, X and N in detail. So those are the same letters that we're using here for confidence intervals. So after we get the point estimate down, then we're going to be learning about confidence intervals, which are a more educated guess. So think of point estimate as a rough guess, and then confidence interval is a more educated guess, but obviously that's going to involve more math. Okay? And then sample size, we're not going to be going over in this video, but if you're interested in it, you're welcome to look through the rest of this section in the book. But in the interest of actually covering everything I need to in this video, we're just going to be focusing on these first two bullet points. Okay. All right, so let's get started with the point estimate. So the point estimate is a single value used to estimate a population parameter or population parameters. The sample proportion P hat is the best point estimate of the population proportion P. Now, remember that P would represent the probability if we randomly select someone from the population, the probability of them being a success, whereas Q would represent the probability of them being a failure. And of course, that's referring to a binomial probability experiment. They don't explicitly say that in the slides, but that's what they're referring to. And the formula for P hat isn't really written in the slides, so I'm just going to write it real quick. It's very easy to calculate. So P hat, obviously we call it P hat because it says P and then it looks like it has a little hat. Okay, so P hat, the formula is X over N. And remember that X is the number of successes. So our numerator is the number of successes. And then our denominator N is the number of trials. So X successes over N trials. On most problems, they will give you P hat, but on some of your homework problems, you might need to calculate it. So just write in the number of successes and then divide by the number of trials or the total number of data values N. And then plug it into your calculator and that will give you P hat. Now P hat is the point estimate. Again, estimate means guess. And a point estimate is sort of like a point that we can start to make a more educated guess from, but this is still a rough guess. So why do we use P hat as the point estimate? We use P hat as the point estimate of P because it is unbiased. And remember, bias is not something that we want to have in our statistical study. So unbiased is always a good thing. And it is also the most consistent of the estimators that could be used to estimate the population proportion P. And if you find all this a little bit abstract, we're going to be going into some examples right away. So, but let's just get through this first. So an unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. So here we're using P hat to estimate the entire population proportion P, or to target it. Okay, so let's see this in an actual real-world example. Okay, so the chapter problem in our book included a reference to a Sallie Mae survey. This is a pretty dated survey, so the numbers are probably higher now, but who knows. Anyway, they have 950 undergraduate college students, and at the time of that survey, they're not saying what year it was done in, but at the time that this survey was taken, 53% of those 950 undergraduate college students said that they take online courses. Now, based on that result, they want us to find the best point estimate of the proportion of all undergraduate college students who take online courses. Okay, so I already erased it, but we know that P hat is X over N. But the thing is, we don't even have X here, and we don't need it. So all we have to do for P hat is just take this 53%. So when they give you a percentage, just remember that we want to write it as a decimal for our homework quizzes and exams. So all we have to do is take this 53%. Because there were 950 people in the sample, the 53% of them that said that they take online courses is going to be the same as P hat. So we don't even have to do X over N here, but I did tell you about the X over N because you might have to do it on some of the problems in our assignments. Okay, But anyway, here p hat is just going to be, remember that the decimal starts right there, and then we move it 2 places to the left. So p hat is going to be 0.53. So that's not too incredibly difficult. And then for your homework, if they don't give you a percentage and they don't give you p hat, just use the formula x over n. Remember that x will be the number of successes, and then n would be the total number of data values in the sample. Okay, so here, because the sample proportion is the best point estimate, we conclude that the best point estimate of p is 0.53. By the way, the sample here would be the 950 undergraduate college students in the study. But what do you think the population would be? Well, the population would have to be all individuals that are of interest. So I would take that to mean all undergraduate college students, potentially in the entire United States, or if they gave us more details, it might be more restricted than that. But I'm going to say the population is going to be a heck of a lot larger than 950. There are hundreds of thousands or even millions of college students, undergraduate college students. Okay, anyway, p hat is 0.53. That's our best point estimate or rough guess of p. And remember, unless we can do a census of all college students, which we're not going to be able to do, we're not going to have enough money to do a census of all the college students, even in one state would be difficult, and in the United States or in the whole world would be not feasible. But we are able to at least make a point estimate very easily. And then what we're learning next is to make a more educated guess. So the educated guess is a confidence interval. So they call it a confidence interval because it's an interval or a range of values that we have a certain confidence for the true value of a population parameter. So here we're using p hat to estimate a population parameter p, but that's just a rough guess. The confidence interval actually gives us a range of values, and after we do the math for it, we're going to know how confident or how sure we are that that range of values actually contains the true value. Okay, confidence interval is sometimes abbreviated as CI. So obviously, if we want to make a more educated guess, we're probably going to have to do more work. Okay, so there's a lot of stuff in these slides. I left pretty much everything from the book in here, but some of this stuff I'm going to go through pretty quickly. So first off, the confidence level is the probability 1 minus alpha. This is the Greek letter alpha, which looks like a lowercase a, but it's actually a Greek letter alpha. The thing is, you're not, in this chapter 7, we're not really going to be doing 1 minus alpha a whole lot. That shows up more in chapter 8, so we'll return to alpha later. So here we're focusing on the confidence level. The most common one is 0.95 or 95%, but other confidence levels would be 99% or 90%. And what the confidence level tells you is how sure you are that your confidence interval actually contains the true value of the population proportion. And you can do this for other population parameters. It doesn't have to be just population proportions, but in this section, we're just focusing on estimating the population proportion P. Okay? So you can also think of the confidence level as the probability or the chance that a confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. Okay? The confidence level is also called the degree of confidence or the confidence coefficient. But that whole slide is kind of wordy. All we really get out of it is it's telling us how sure we are that our educated guess is correct. Okay? So the common confidence levels are 90%, 95%, and 99%. It's actually possible to do the math to calculate what's called a critical value for other confidence levels, but these are the three most common confidence levels. And all of our problems in the homework, quizzes, and exam are going to be one of these three, because that's all that they have on MyMathLab. Okay, and then in Chapter 8, we'll be talking about alpha. Alpha is the same as 1 minus the confidence level. So, for example, if you have a confidence level of 0.90, that's going to correspond to alpha equals 0.10. 0.95 corresponds to 0.05. So all they're doing is, if you do 1 minus this number, you get alpha. Alpha is also known as the significance level, but again, it's not that important in Chapter 7. It's more important in Chapter 8 when we're doing hypothesis tests. So we're going to kind of just focus on the confidence level because that's all we really need here. Okay, now critical values. I left this in the slides in case you're wondering how to calculate a critical value. But I'm going to skip over this quickly because you don't really need to do it in your homework. I did want to talk about what it means, though. So for the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly high or significantly low from those that are not significant. Okay, and that's why alpha is actually called your level of significance. And then the picture looks like this. So the number z sub alpha over 2, which is the same as your critical value, separates an area of alpha over 2 in the right tail of the standard normal distribution. So what they're saying is your critical value is just a z-score, and they're calling it z sub alpha over 2. And all it means is that the area to the right of alpha over 2, of z sub alpha over 2 is alpha over 2. And then this area down here, which is the area to the left of negative z sub alpha over 2, is also alpha over 2. So the reason they're calling it alpha over 2 is half of the area is down here, and the other half of the area is up there. Okay, but the thing is, these critical values, for us, in our assignments, we're not going to have to calculate them. So you can calculate them the way they did in the slides. So if alpha is 0.05, your confidence level is 95%. And then you can find the critical z-score by looking at that picture we were just looking at. And so that's actually how you get critical values. If you want to calculate them by scratch, but we don't really have to do that in our class. So the thing is, if your confidence level is 95%, that means the area in both tails, when they say both tails, they mean the tail on the right and the tail on the left. So those two green areas. The area in both tails is 0.05, alpha equals 0.05, which means the area in the right tail is alpha over 2, which is 0.025. So the cumulative area from the right, excluding the right tail rather, is 1 minus 0.025, which is 0.975. So the book makes this seem a lot more complicated than it needs to be. They're just saying that if you look at this left tail right here, the area to the left has to be 0.025. And then this area to the right over here is also 0.025. So that means the total area to the left of this z sub alpha over 2 is 0.975. And then if you look that up in table A2, you're going to get your z-score of 1.96. But rather than having to draw this picture and worry about alpha and all that, the easier thing to do for our class is just to not calculate it, but rather to use table A2. So the previous example shows in great detail how a 95% confidence level results in a critical value of z sub alpha over 2 equals 1.96. However, I don't recommend going through all of that because you don't need to. On your homework quizzes and exam, you want to use your confidence level, which will be given to you in the problem. So your confidence level will either be 90%, 95%, or 99%. And then in the bottom right corner of table A2, you're going to be able to find each critical value. So the critical value, z sub alpha over 2. For 90% confidence level would be 1.645. For a 95% confidence level, our critical value would be 1.96. And for a 99% confidence level, our critical value is 2.575. And then in chapter 8, we'll talk more about alpha, which is a significance level. But like I said, it's not that important. So mainly just focus on confidence level and the critical value. And rather than always having to use this slide, you can just, like I said, you could just open up table A2. If you look on the page that says positive z-scores, oops, that was not the button I meant to press. If you look on the page that says positive z-scores from table A2, and then we go down to the bottom right corner, here we're going to see we have all of the common critical values. So that whole thing that they were doing where they were drawing the picture isn't really needed. Okay, so you've got them all here. So confidence level of 0.90 gives you a critical value of 1.645. 0.95 gives us 1.96. 0.99 gives us 2.575. So hopefully that's not too bad. Okay, so let's go ahead and move along because these slides are quite long. So gotta keep moving here. Okay, so returning to the slides, just remember this is in table A2 in the bottom right corner. All right, so probably the most math-intensive thing that we have to learn in order to do an educated guess about our population proportion is the margin of error. So the margin of error is written as capital E. Obviously, E stands for error. And margin means how much room we need in order to have our level of confidence that our guess is actually correct about the population proportion. Okay, and the formula is E equals z sub alpha over 2. So z sub alpha over 2 is the critical value that we were just talking about. And you're always going to be looking that up in the bottom right corner of table A2. Okay, and then probably the part that's a little bit more math intensive, just remember that the critical value is always going to be one of those three numbers in our class, the ones that we were just looking at. The more math intensive part is this. So the estimated standard deviation of sample proportions. Turns out that the estimated standard deviation, long story short, works out to this. So I know that looks a little bit intimidating, but it's actually really not too bad to calculate. So it's something that you're going to put into your calculator. It's going to be the square root of p hat. We've already talked about p hat. So p hat is the sample proportion, which they'll either give to you in the problem, or you can calculate as x over n, where there are x successes and n trials. And then q hat is 1 minus p hat, which should make sense. If you think back to section 5.2, in section 5.2, we said that q is 1 minus p, so it should make sense that q hat equals 1 minus p hat. It's really the same formula, it's just that the little hats mean that we're talking about our sample only, not the whole population. Okay, so looking at this formula, p hat we've already talked about. Q hat we can get, once we have p hat, we just do 1 minus p hat to get q hat. And then n we've also already talked about. N is the number of trials or the number of data values. Okay. So hopefully that's not too bad. And the book says that this is called a walled confidence interval. And the margin of error is basically how much room we need to make sure our estimate, that we're confident to the level we need to be about our estimate or our guess. I'm not going to cover part 2 of this section. In our book, if you're interested in it, they have other methods for constructing confidence intervals, but in our class, we're going to focus on the walled confidence interval for proportions, which is this formula right here. Okay, now, before we actually do a whole example of all that, I wanted to talk about what confidence intervals mean. So a confidence interval is going to be in a certain format. For example, one of the problems in this section in our book, they end up with this. This is an example of a confidence interval, sometimes abbreviated CI. So as you can see, you have a value on the left, a value on the right, and then you have P in the middle. So this confidence interval represents a range of values. So it's saying that the population proportion P, which we're trying to estimate, is greater than 0.405 and less than 0.455. And there's really only one correct way of reading this. So for example, for this particular example from the book, if this confidence interval has a confidence level of 95%, the correct way to say it is we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. So the whole point of this slide and the next few slides is to make sure that when you're doing your homework quizzes and exam, that you choose an answer that's in this format. So it might be 90% confident or it might be 99% confident, but it needs to be worded pretty much in this way to be correct. There are a lot of incorrect ways of interpreting a confidence interval. So let's see some of those incorrect ways on the next slides. So on this slide, this is an example of a wrong way of saying or interpreting a confidence interval. So if you say there is a 95% chance that the true value of P will fall between 0.405 and 0.455. So the reason that's wrong is basically it's making it sound like P is changing, which is not. Okay, P is not changing. P is fixed. We just don't know what P is. P is the population proportion. We just have a sample though. But P is fixed. We just don't know the true value of it. But it's not changing. Okay, so that's why that's wrong. Okay, another wrong way of interpreting a confidence interval is to say 95% of sample proportions, remember sample proportions are p hat, will fall between 0.405 and 0.455. So the reason that one's wrong is it's making it sound like we're estimating the sample proportion p hat rather than the population proportion p. So p hat is going to be fixed. So the reason the first one is correct and the other ones are wrong just comes down to what makes sense mathematically. So even if you don't understand why the other ones are wrong and why this is correct, you can at least look for this wording on your homework quizzes and exams and know that this is correct. It's the correct way to say it. Okay, and if you're wondering a little bit more about why it's correct, they have a nice explanation here in our book. So a confidence level of 95% tells us that the process we are using should in the long run result in confidence interval limits that contain the true population proportion 95% of the time. So that if our confidence level is 95%, then that would mean on average, out of all of the confidence intervals, that would mean that on average, only 5% of them wouldn't contain the true population proportion. So the process kind of should make sense that what we're really choosing is not p and not p hat. What we're choosing is different confidence intervals. And this green confidence interval would be one that did not contain the population proportion. But that's just a nice picture here, because it kind of gives you an idea about what they mean to be 95% confident. That means 19 out of 20 times our confidence interval is going to work, and it contains the true value of the population proportion. So that interval actually does contain the true value of the population proportion p. That's the correct way. Okay, but wordiness is always can be confusing, but hopefully that's helpful. All right, so let's actually jump into constructing a confidence interval to estimate a population proportion p. We've talked about it, but let's talk about it again. P is a population proportion. P hat is the sample proportion. You can use x over n if that's not given to you in your homework. N is the number of sample values or the number of trials. E is the margin of error. That's what we're going to have to use that formula for. Q hat, we already said, was 1 minus p hat. And then z sub alpha over 2 is the critical value, which you can just look up in the bottom right corner of table A2. Okay. In order to construct a confidence interval for population proportion p, your sample has to be a simple random sample. The conditions for the binomial distribution have to be satisfied. So there have to be a fixed number of trials n. The trials have to be independent, which means that for each trial, the chances of one can't affect the chances of another one. All right, and then there are two categories of outcomes. So we call one category success and the other category failure. The probability of a success is p, and the probability of a failure is q equals 1 minus p. This is all stuff from 5.2, so feel free to rewatch my video or review your notes from 5.2 if you need to. Okay, and the probabilities have to remain constant for each trial, just like in 5.2. So basically, it just has to be a binomial distribution. Okay, and then an interesting requirement is in order to use, what we're doing is we're actually going to be using a normal distribution to approximate the binomial distribution. And in order for that to work, we have to also have the added requirement that there are at least 5 successes and at least 5 failures. So remember, x is the number of successes, and then n minus x is going to be the number of failures. However, once again, on your homework quizzes and exam for this class, this requirement, I believe, is usually satisfied. So it's not really going to be too much of an issue. All right. So to do a confidence interval, the hard part, well, not the hard part, but the complicated part is calculating the margin of error E. So that's what we're going to do first. And then after we have the margin of error E, it's quite straightforward to actually write out the confidence interval estimate, which is p hat minus E is less than P is less than P hat plus E. And there are other ways you can express the confidence interval. You can express it as p hat plus minus E, or p hat minus E, comma, p hat plus E. Okay, now the round off rule for confidence interval estimates of P. Round the confidence interval limits for P to 3 significant digits. Okay, so we're going to be rounding not to 3 decimal places, but 3 significant digits. So starting with the first non-zero digit, we need to have that digit and then 2 more, and we round. Okay. All right, so if you verify those requirements and you have the critical value, then you can do the margin of error, and then we'll be able to write the confidence interval and then round the result. So it's going to be a 5-step process, but it's really easier to just go into the example. We can come back to this. All right, so example, returning to the Sallie Mae chapter problem, we said that p hat was 53% or 0.53. And then because there were 950 undergraduate students in the sample, n equals 950. So first off, for part A, we're going to go ahead and find the margin of error E that corresponds to a 95% confidence interval. Okay, so if we go back to this slide right here, the margin of error E equals z sub alpha over 2 times the square root of p hat q hat over n. Okay, so let me write that down. So margin of error E equals z sub alpha over 2. Remember, z sub alpha over 2 is the critical value times the square root of p hat q hat over n. Okay, and obviously we need to figure out what z sub alpha over 2 is in order to plug it in. So either on the bottom right corner of table A2, or if you want to go back to the slide where I summarize the margin of error, if our confidence level is 95%, then our critical value z sub alpha over 2 is 1.96. Okay. So hopefully that's not too bad. So that was the view I meant to put it in. Because they said a 95% confidence interval, that means our critical value z sub alpha over 2 has to equal 1.96. Okay, and then in order to plug everything in here, we also need p hat, which we showed in an earlier example for this problem. P hat we said was 0.53. And then we also need q hat, which is 1 minus p hat. Okay, so here q hat is going to be 1 minus p hat, so 1 minus 0.53. Oops. Oh dear. That really smudged. Okay, so 1 minus p hat is going to be 1 minus 0.53. So either in your head or on a calculator, you're going to see that q hat equals 0.47. Okay. And then n, we said, was 950. So I'm going to go ahead and write that down as well. So now what we can do is we can just plug everything in to this formula on the right side of the formula, and that will give us our margin of error E. Okay, so the z sub alpha over 2 is 1.96, and then we have the square root of p hat, which is 0.53, times q hat, which we calculated is 0.47. Okay, all over n, which is 950, because there were 950 undergraduate students in the study. So now, with your calculator, you may be able to just type this in all at once. That's how I would do it on my calculator. So actually, let me rewrite it as the way I would type it into my calculator, just in case that's helpful to you. So because there's two factors in this numerator here, I would press the multiplication button in between those two factors, and I would put parentheses around this numerator here. Okay, so on my calculator, I would just type all of this in directly. So I would do 1.96, which is our critical value, and then I press the square root button. If it doesn't accept that, you can put in a times here. So it's 1.96 times the square root, and then I'm going to put the fraction button, and in the numerator of my fraction, I'm going to have parentheses 0.53 times 0.47, and then in the denominator, I have 950. And there are other ways of typing this in. I'm not saying this is the only way to type it in, but this is how I would type it into my calculator. You're going to have to get comfortable with whatever calculator you're using for our class. So you may type it in a somewhat different way, but there's lots of videos on YouTube on how to use calculators. Okay, anyway, our margin of error E that I'm getting here, I'm not going to round it yet. I'm going to go ahead and write out a lot of digits. So we got E equals 0.031738. 0.031738. Now, if they ask us to round it, like in our homework, we do need to round it. But right now, I'm just writing out a lot of digits. Okay, so if we return to the slides, this button would work. Okay, we just found the margin of error E. It's also worked out on the slides. We didn't bother to do the requirements because those are already satisfied in all of our homework problems. But the margin of error, as you can see, they went ahead and wrote out a bunch of digits like we did. And then you just need to read your homework problem. If they're asking for the margin of error and they're asking you to round it, then you need to round it to what they say. But in general, if they're not asking you to round it, then you want to just write out a bunch of digits so that you don't end up with rounding error. Okay, and then let's take a look at part B. So part B is going to be to find the 95% confidence interval estimate of the population proportion P. So the formula for this, the standard formula that people use is this one right here. P hat minus E is less than P is less than P hat plus E. Okay. So in part B, the confidence interval, I'm just going to write CI, stands for confidence interval. The format is P hat minus E is less than P is less than p hat plus e. Okay, so remember we already calculated 0.53 is p hat, and we just calculated e. So you just have to plug in the numbers into your calculator to get the left side and the right side of this confidence interval. So on the left side, p hat minus e is going to be 0.53 minus 0.0317381. So 0.53 minus 0.0317381. Okay, so if you do p hat minus e on your calculator, just doing this minus that, I got 0.498, and I'm going to go ahead and round to 3 significant digits. So 0.498 is this. This is less than p, which is less than, let's do p hat plus e on our calculator. So p hat plus e is going to be 0.53 plus this number here. So type that into your calculator, 0.53 plus 0.0317381 gives us, after we round it, 0.562. So I rounded to 3 significant figures. So this right here that I'm boxing is our answer to part B. Actually, let me move this up here so it makes more sense. So this is part B. It's our confidence interval. Okay, and then if we go ahead and return to the slides, while I erase all this, you can see that they got the exact same numbers we did using that same formula. So notice that they did the same thing we did, where they used E with a bunch of digits. So they didn't round until they were actually at the end there. So they did the 0.53 minus E minus 0.317381, and then the p hat plus E. And then at the very end, they rounded to 3 significant figures. And then I wanted to point out, as you can see here on this slide at the bottom, the same result could be expressed in another format, which would be, you can also write it as, this is p hat plus minus e. That's what this is. So 0.53 plus minus e. Or instead of writing 0.498 is less than p is less than 0.562, you can write it as an interval with parentheses. And you just separate the lower boundary, 0.498, and the upper boundary, 0.562, with a comma. And if we want the 95% confidence interval for the true population percentage, we could express the result as 49.8% is less than p is less than 56.2%. And remember that p actually represents the population proportion. So we don't know the population proportion because we can't do a census. But what's powerful about this is just on our sample with 950 students, assuming it was a simple random sample and we did our math correctly, we're 95% sure that for all college students in this population, which is presumably maybe all the colleges, undergraduate colleges in the United States, the percentage of people taking online courses at the time that study was done is between these two numbers. So that's incredibly powerful. I don't know if you can see that, but it really is powerful. That you just have a sample, but then you're able to make conclusions about a whole population. So this is called inferential statistics. And even though it's a ton of work to use all the formulas, it's worth it because you're making an educated guess that's really helpful in science. It's really helpful in general. So now I want to go to part C because they ask us a question that we haven't looked at yet. So I don't know what happened with the lettering here. They're not showing up on the slides. But anyway, we've already done part A, which was the margin of error. And then we also did part B, which was the 95% confidence interval. And then part C, we need to answer this question. Okay, so based on the results in part C, can we safely conclude that more than 50% of undergraduates take online courses? And obviously they're talking about at the time the study was done. And then assuming that you are an online reporter, write a brief statement that accurately describes the results and include all of the relevant information. So I'm thankful that the book has a nice, long, worked out set of answers to this, because I don't like writing essays, and you probably don't either. Well, some of you may, to each their own. But when you're doing your homework quizzes and exams, when you have questions like this, there will be multiple choice. You're not going to have to type it in. You're going to look for stuff like this. So what they say in the book is, based on the confidence interval obtained in Part B, we cannot safely conclude that more than 50% of undergraduates take online courses. So why are they saying that? Well, if we're saying more than 50% of undergraduates take online courses, the problem with that is we're 95% sure that the population proportion is between 49.8% and 56.2%. Well, the problem comes in on the lower side here, on the bound on the left. So the problem is we can't safely say that it's greater than 50% because there's a good chance that it could be below 50%. For example, if it's 49.8% or 49.9% or any decimal in between. Okay, so that's why they're saying you cannot safely conclude that it's more than 50% because the confidence interval ranges from 49.8% to 56.2%. It is possible that the population percentage is below 50%. Okay. So hopefully that makes some sense. Summary of results. This is if you were a reporter and you were trying to write a story about your statistics. Here is one statement that summarizes the results. 53% of undergraduates take online courses. Well, when they're saying that, that's the point estimate. Okay. That's not the population proportion P, that's our point estimate P hat. That percentage is based on a Sallie Mae survey. So the 53% they're talking about is P hat of 950 randomly selected undergraduates. In theory, in 95% of such polls, in other words, we're 95% confident, the percentage should differ by no more than 3.2 percentage points in either direction. So the 3.2 percentage points is the same as the margin of error. So remember that the margin of error E, we said was 0.0317 or about 3.17%. So they rounded that to 3.2%. All right, and that's pretty much the long way of describing everything that we've already studied. Okay, so cool. And then that is that's good fun, and I hope you enjoy the homework and quizzes from this section. And I hope this video was, as always, I hope it was helpful. I'll see you next time.